Download this code from codegive.com, link in the description below. Coda file system, a comprehensive tutorial. The Coda file system is a distributed, fault-tolerant, and highly available network file system designed for mobile computing and challenging network conditions. It's a direct descendant of the Andrew file system, AFS, and builds upon its core concepts while introducing several improvements. This tutorial will delve deep into the Coda file system, covering its architecture, features, operation, and how to interact with it. We'll also provide code examples to illustrate key concepts. Core concepts and architecture. Coda addresses the inherent challenges of mobile computing, where network connectivity is often unreliable or unavailable. Its design focuses on providing persistent access to data even when disconnected and synchronizing changes when connectivity is restored. Here's a breakdown of the key components. Coda servers. Venus Coda servers store the actual data files. They operate in a clustered environment for redundancy and availability. They're responsible for serving file access requests, managing replicas, and handling updates. Think of them as the source of truth for the data. Coda clients. Venus the client component runs on individual machines, desktops, laptops, mobile devices. It's responsible for caching files locally, managing disconnected operations, and communicating with the Coda servers when online. The Venus process on the client acts as the intermediary between the user applications and the Coda file system. Volume. A volume is a logical grouping of files, similar to a directory tree. It's the unit of replication and management in Coda. Volumes can be independently managed and replicated across servers. Disconnected operation, hoarding/reintegration. Coda's signature feature. While connected, the client hoards relevant files and directories into its local cache. When disconnected, the client continues to operate using the cached copies. Upon reconnection, the client reintegrates any changes back to the servers. This ensures minimal disruption even without network connectivity. Replication. Data is replicated across multiple servers for redundancy. If one server fails, the client can still access data from other replicas. Callbacks. Servers send callbacks to clients to notify them of changes to files or directories that they have cached. This allows clients to invalidate stale cached data and keep their caches consistent with the server's view. Optimistic concurrency control. Coda uses optimistic concurrency control. Clients make changes to cached copies assuming that conflicts are rare. When reintegration occurs, the system detects and resolves any conflicts. Visual representation. 2. Operation and workflow. Here's how a typical interaction with the Coda file system unfolds. 1. Mounting the Coda file system. The client's Venus process needs to be configured and pointed at the Coda servers. This is typically done by mounting the Coda file system at a specific mount point, example/Coda. 2. File access. When a user application requests a file, the client's Venus process first checks its local cache. Cache hit. If the file is present in the cache and the cache entry is considered valid, based on callbacks or timeout, the file is served directly from the cache. This is the fastest scenario. Cache miss. If the file is not in the cache or the cache entry is invalid, the Venus process contacts a Coda server. The server provides the file data, and Venus stores it in the cache for future use. 3. Disconnected operation. If the network connection is lost, Venus enters disconnected mode. It continues to serve files from the cache. Any modifications to files are recorded locally in the cache. 4. Reintegration. When the network connection is restored, Venus automatically attempts to reintegrate any changes to the Coda servers. Asterisk conflict detection asterisk the server compares the client's modified version of the file with the current version on the server. If there are conflicts, a conflict resolution process is triggered. Asterisk conflict resolution asterisk Coda offers various strategies for conflict resolution, including asterisk last writer wins asterisk the most recent version of the file is accepted. This is the simplest, but can lead to data loss. Asterisk manual resolution asterisk the user is prompted to manually resolve the conflicts by merging the different versions. Asterisk version control integration asterisk integration with version control systems, example Git, can help automate conflict resolution. 5 callbacks asterisk when files on the server are modified by another client, the server sends callbacks to all clients that have cached those files. This tells the clients to invalidate their cached copies, ensuring that they fetch the updated version the next time they access the file. 3. Practical examples end code. While direct interaction with Coda servers through custom code is rare, you typically use standard file system calls. We can illustrate some concepts using system calls and by examining tools that interact with Coda. Mounting the Coda file system, illustrative. The actual mounting process depends on the operating system. Typically, a command line utility, example mount, is used. Here's a conceptual example. This command tells the system to mount the Coda file system located at coda_server_address:/, the root volume on the Coda server, at the mount point mount_point, example/Coda. The T-Coda option specifies the file system type. Replace coda_server_address and mount_point with the actual values. B standard file system operations, C/C++. Once the Coda file system is mounted, you interact with it using standard file system calls like open, read, write, close, stat, mkdir, etc. These calls are handled by the operating system kernel, which then communicates with the Coda client, Venus, to access the data. Explanation asterisk. Asterisk the code includes standard header files for file I/O and system calls. Asterisk it defines the file name using /coda/my_file.txt, assuming that /coda is the mount point for the Coda file system. Adjust this path according to your mount configuration. Asterisk open, opens the file for reading, O_writtenly. Error handling is included. Asterisk read, reads up to size of, buffer, 1 bytes from the file into the buffer. Error handling is included. The buffer is null terminated to make it a valid C string. Asterisk printf, prints the contents of the buffer to the console. Asterisk close, closes the file. Error handling is included. Asterisk stat, gets the status of the file, size, modification time, etc., and stores it in the file_stat structure. Asterisk the code prints the file size. Important asterisk this code snippet operates after the Coda file system is already mounted and running. The Coda client, Venus, handles the communication with the Coda servers behind the scenes. See volume management, conceptual. Coda provides tools for managing volumes, but these are typically command line utilities rather than direct API calls you'd use in your own programs. Here's a conceptual outline of how volume management works. 1. Creating a volume asterisk. This command might create a new volume named my_volume and replicate it across the Coda servers server 1 and server 2. 2. Setting volume permissions asterisk. This command might grant the user Alice read, write, and execute permissions, RWX, on the volume my_volume. 3. Moving/replicating a volume *. This command might move a replica of the volume my_volume to the Coda server 3. D. Monitoring Coda status, illustrative. Coda provides utilities for monitoring the status of the client and server processes. These usually involve examining log files or using command line tools. *Client status, Venus. You can typically check if the Venus process is running using system commands like ps or systemtl. You can also look at Venus's log files for error messages or other information. *Server status. Coda servers usually have dedicated monitoring tools that provide information about server load, network connectivity, disk usage, and other metrics. Again, these are typically command line tools. 4. Advantages and disadvantages. Advantages *. Disconnected operation * provides seamless access to data even when offline. This is the key advantage for mobile users. High availability * replication ensures that data remains accessible even if some servers fail. Fault tolerance * the system can tolerate server failures and network interruptions. Scalability * Coda can be scaled to handle a large number of users and files. Security * Coda includes access control mechanisms to protect data from unauthorized access. Data consistency * callbacks and reintegration help maintain data consistency across the system. Disadvantages * complexity * Coda is a complex system to set up and manage. Conflict resolution * handling conflicts during reintegration can be challenging, especially with complex file types. Overhead * the overhead of caching, replication, and callbacks can impact performance, particularly in environments with high network latency. Development activity * while Coda has a strong legacy, active development and community support have slowed down in recent years compared to other distributed file systems. V. Alternatives to Coda. While Coda remains a valuable concept and has influenced many systems, there are other distributed file systems that are more actively developed and widely used today. AFS, Andrew file system, the direct ancestor of Coda. Still used in some environments. NFS, network file system, a widely used file sharing protocol for Unix-like systems. SMB/CIFS, server message block / common internet file system, the standard file sharing protocol for Windows systems. *CEF*, a modern, scalable, and fault-tolerant distributed storage system. *GlusterFS*, another open-source distributed file system. *HDFS, Hadoop distributed file system designed for large-scale data processing with Hadoop. Cloud-based storage, Amazon S3, Azure Blob Storage, Google Cloud Storage. These provide highly scalable and reliable storage services. While not strictly file systems, they often provide file-like APIs and are commonly used for storing data in the cloud. 6. Conclusion. The Coda file system introduced groundbreaking concepts for distributed file systems, particularly in the area of disconnected operation. While its active development may have slowed, its core principles continue to influence the design of modern distributed storage solutions. Understanding Coda provides valuable insights into the challenges and trade-offs involved in building robust and reliable file systems for mobile and distributed environments. This tutorial provides a comprehensive overview and includes practical examples to help you understand and potentially explore the Coda file system. Remember to adapt the code and commands to your specific environment and refer to the Coda documentation for more details.